Again, hi everybody. Hope all of you are staying safe. No one's getting sick. Let's go ahead and get started. So today we're going to be covering the beginning of the logic section from the textbook. Now, for my notes, I'm going to be using the Rosen discrete mathematics book. In today's lecture will be sections 1.1 and 1.3, probably. Again, you don't have to purchase that book, but as far as my lecture notes are, that's the book I'll be using. Okay, so let's get started. This logic, and in particular, we're going to be looking at what's called propositional logic. So the first definition, of which there's going to be quite a few definitions in this lecture, will be that of a proposition. So definition, a proposition is a declarative statement that is either true or false. Okay. So true, I'm going to denote with a capital T, or false, which I'm going to denote with a capital F. Okay. Now, propositions cannot be both true and false at the same time. They are strictly one or the other. Okay. So, as an example, we can look at something like UHD is a public university. Okay, so that's an example of a proposition. It's declarative, right? And it has a truth value that's associated with it. So here, this is a true proposition, right? So what we can say is that this is a true proposition. And we'll learn what this triple equal sign means in a bit. So propositions do not have to be true. For example, someone give me a false proposition. You can say it out loud or send it to me in the chat. So come up with
the sky is red.
The sky is red. Okay. Yeah, this would be a proposition. It's declarative, right? And it's either true or false. It happens to be false, right? Okay. So now, when dealing with propositions, we're going to want to work with them almost like in an algebraic manner. And when we do that, we're not going to write out entire propositions like this. What we'll do is we'll say that, like here, this first proposition, we could call lowercase p. And then this proposition here, we can denote that by q. So we will typically use lowercase letters like p, q, r, s, t to denote entire propositions. So P is the proposition UHD is a public university. And it happens to be the case that P is true. Q is the proposition the sky is red, which happens to be false. Okay? Simple enough, right? Mm-hmm. So now we're going to define various operations on these propositions. So I'm going to go ahead and erase this. Okay, so definition. So the negation of a proposition P is the proposition it is not the case that P. Okay, so I should probably note the notation here. So the negation of P is written like that. So this right here reads as not P. Okay? So with our previous propositions that I erased, the P and the Q, the negation of P would have been, it is not the case that UHD is a public university. Now that is a false proposition, which leads me to our first, what's called the truth table. So here's P, and here's not P. And so if P is true, then the negation of P is going to be false. If P is false, the negation of P must be true. So it's a fundamental fact of propositions that you just have to remember that if you negate the proposition, you get a proposition with the opposite truth value. So in the case of the Q that I erased, the sky is red, the negation of Q would be, it is not the case that the sky is red. Or just simply, the sky is not red, which would be a true proposition. Again, if the original was false, the negation will be true. Okay? Make sense? Okay, so now that we have this operation here, I'm going to define the rest of the operators that we'll be dealing with when considering logic. Okay, so it's going to take me a second to write down. So, P, Q. So there are possible combinations of truth and false when you have two separate propositions. So they can both be true, right? P can be true, Q can be false. P can be false, Q can be true, and then they can both be false. Okay? And those are all the possible combinations of true and false between these two propositions. Okay. So our first operation that we're going to define is called the disjunction of P and Q. So this is called disjunction. Okay. And this reads P or Q. Okay. Now the disjunction between two propositions is true whenever at least one of them is true. Okay. So here, if P and Q are both true, then yes, that's going to be true. If P is true and Q is false, then still true. false or true, still true, false or false, false. Okay? So this is the disjunction, and I'll typically just say P or Q. Okay? Next up, we have the conjunction. Conjunction. Okay? And this reads P and. Okay? So the conjunction is true only when they're both true, and false every time. So here we have true and true, which is going to be true. True and false is going to be false. False and true is going to be false. False and false is also false. Okay? So, and the end will make sense when you consider it when dealing with actual propositions. So like with the P and the Q that we had earlier that I erased, UHD is a public university was P. Q was the sky is red. So if you read that, UHD is a public university and the sky is red, that's false, right? Because the second proposition would be false. Whereas if you look at the or, right? UHD is a public university or the sky is red, at least one of those is true, so it would always be true. Okay? All right, so up next, we have the conditional. It's called the conditional. And this reads several different ways. Reads first, if P, then Q. If P, then Q. And it also reads P implies Q. So I'll use those interchangeably. So if P, then Q, or P implies Q. Okay. Now, the conditional, more terminology before I move on. So here, the first proposition is called, let's see. The first proposition is called the hypothesis. Okay? And the second proposition here, that's called the conclusion. Okay? Now, the conditional is only false when you have a true hypothesis and a false conclusion. Every other time it's going to be true. So if you look here, we see true implies true, true. True implies false, false. False implies true, true. False implies false, true. It's only false in one instance, when you have a true hypothesis and a false conclusion. Okay? In particular, you should really make note that whenever you have a false hypothesis, you're going to have a true conditional statement. Okay? And one more. So this is called the biconditional. No. Biconditional. And this reads P if and only if P if and only if Q. Now, the biconditional is going to be true whenever P and Q have the same truth value. So we see true if and only if true, they both have the same truth value, so it's going to be true if and only if false, false, because they don't have the same truth value. False if and only if true, again, false. False if and only if false, true, because they have the same truth value. Okay? So these are the basic, what I call operators on these propositions. The or, the and, the conditional, and the biconditional. Okay? Whenever you have several propositions that have been combined using these operations, these are called compound propositions. But I'll typically just say proposition and I'll drop the compound. But whenever you have more than one, your textbook might call it a compound proposition. Okay? So, hopefully everyone's good. Just a bunch of definitions so far. We haven't done anything operational yet. Okay. Now, let's see. Another definition. Okay. So, two propositions are logically equivalent so two propositions, I'll say P and Q, are logically equivalent and this is written P triple equals sign Q whenever P if and only if Q is always true. Okay. Now, I need to introduce two more definitions now, because what it means to always be true is something kind of special. So let's go ahead and do that now. A proposition or a compound proposition that is always true is called a tautology. Okay, so tautology. A proposition that is always false is called a contradiction. Okay. Okay, so, and a proposition that is neither a tautology nor a contradiction, so it can be true, it can be false, is called contingency. So going back up to the first definition, we write two propositions are logically equivalent whenever the biconditional between them is a tautology. Okay? So let's look at some examples of tautologies and contradictions. Okay, so A, I'll do like false, Q, B, true, and let's say P, and then one more here. Okay, so A, B, and C. So which one of these would be a tautology? Any guesses?
F or Q.
B.
B, right? Whenever you have a false hypothesis, it's always going to evaluate to be true, right? It doesn't matter what the truth value P happens to be. This is always going to be true, okay? So this is a tautology right here. Which of these is a contradiction?
C.
Which one? C?
E.
So B is a tautology. That one's always true, no matter what you plug in for P. If P was false, so I see C. And so C here, this is a contradiction. Because the conjunction, right, or the and operator, in order for this to be true, both of the propositions have to be true, right? But that's always false, so it doesn't matter what Q is going to be. This is always going to evaluate to false. Okay? And then here, this is a contingency, because the truth value of this compound proposition depends on Q. If Q is true, then this will be true. If Q happened to be false, then this would be false. So it depends on the value of Q. Whereas these here, no matter what you plug in, you're always going to get the same end result. In this case, you're always going to get true no matter what P is. In this case here, you're always going to get false no matter what Q is. Okay? All right, so let's see a case where we have two propositions that are logically equivalent. Okay, so my claim is that the conditional, if P then Q, I claim that that's logically equivalent to not Q implies not P. Okay. So in order for this to be true, right, if I'm going to write that, then it has to satisfy the definition of logical equivalence, right? So what this is really saying is that, well, it's like a question that we have to answer. Is P implies Q if and only if not Q implies not P a tautology? Okay. If we can verify that this biconditional is a tautology, then we can say that this claim is true. So one way to do that, and this is I guess, an instance of a proof, actually, is to use a truth table. Okay, so I'm going to go ahead and write proof. So what I'm going to do, I'm going to make a rather large truth table. Here's P, here's Q. So we have true, 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 false, 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 and then, oh yes, sorry, false, true, and then finally false, false. Okay. All right, so we have if P then Q, and then we also have not Q implies not P. Okay. So we can fill this one out. There's only one case where the conditional is false. All other cases are true. All right, so then we can take a moment to look at this. So we have the negation of Q implies the negation of P. All right, so it's like saying not this implies not this. Okay, so not that is false, not that is false, right? So my first entry here is going to be false implies false, which is true. My entry here, so I negate that implies a negation of that. So it'd be true implies false, false. And then here we have false implies true, true, again, and then true implies true. Okay. Now, notice now, if we look at this biconditional here, remember the biconditional is true whenever the two propositions have the same truth value. Well, here, true if and only if true, because we're looking at that, if and only if that, that, if and only if that. So true if and only if true, true. Oh, I don't know why I put a period there. False if and only if false, true. True if and only if true, true. True if and only if true. So notice now, here, right? No matter what the values of P and Q are, when we look at this biconditional statement, we always get true, right? So this is a tautology. It's always true, no matter what happens, right? Which means yes. We can write that logical equivalence up there. Now, you don't necessarily need to actually fill out this column here, because you can just look right here and just look at these two columns, and they match up. They're the same, right? So you can finish it there. Okay. Any questions on that? Okay. Okay. So I think that'll be it for today's lecture, but I'm going to give you one problem to do on your own. You don't have to turn it in or anything, just verify that you know how this stuff works. So I have a claim that if you negate the disjunction of P and Q, that's logically equivalent to the negation of the conjunctions. So using a piece of paper, verify this logical equivalence using a truth table, and that's it. Okay? Okay.
Verify using De Morgan's law.
Okay, so 1 second, I got a question here. Can I explain second class negation? Can you elaborate on that question that I got in the chat? I see second last.
Professor, I was asking for the second one, the negation. That true is true. Then true, false is false. That thing that you showed. But you just rubbed that, so.
Did I just erase?
Yeah, you just erased.
So I think you're asking about the column associated with this, right?
Yes, sir.
Okay, so true, 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 false, false, true, false, false. Okay, so not Q implies not P. So look to the Q here, negate that. What do you get? False, right?
Yes, sir.
And then you negate that, you get false. So false implies false, which is true. Here, you negate this, and it becomes true, right?
Right.
You negate that, it becomes false. So then you have true implies false, which is false. Here, you negate that and negate that, so you have false implies true, which is true. And here we have true implies true, which is true.
So in this case, the Q will be the conclusion, right?
Here?
Yeah.
Yeah, so in the original conditional, Q is the conclusion. But over here, the hypothesis is not Q. And the conclusion here is not P.
Okay.
Yeah, it's like reading left to right. We're like, this is the first thing, so that's going to be the hypothesis of this conditional.
So in this case, we have to focus on the conclusion. That is negation P.
You have to focus on both of them. Both, yeah, not Q and not P.
Okay.
Because in order for this to be false, you need to know something about the hypothesis. Not Q has to be true, and not P has to be false. And then just to reiterate with this one here, true implies true, true implies false, false implies true, false implies false, true. And then we see quickly here that these have the same values, so these are logically equivalent.
Okay, sir. Thank you so much.
Yeah, you're welcome. And you would use that idea to show that. So, for example, you might have something like this, right? Like P or Q, and then not P or Q, and then not P and not Q. And then you just fill those columns out, and then you should get that this column and this column are the same. And then once you get that, you've proven that to be true. Okay? Okay, so that'll be it for today's lecture. And hopefully it wasn't too boring. I know there's a lot of definitions right now. Just please be sure to keep up with the Zybook, work through it, read through it. And the homework, I think, is due next Saturday or something like that. I'll double check, but I think it's due next Saturday.
It shows the 13th.
Yeah, the 13th.
Okay, so it's due on the 13th. So you have a decent amount of time, but try not to get too far behind. Probably next lecture, we're going to pick things up quite a bit. I'm going to move fast, so just be ready for that. We'll be talking about logical equivalencies and how to prove them without truth tables. Okay, and then maybe starting next week, I'll start adding in Python programming lectures. Okay. All right,
Sure.
that'll be it. Everyone stay safe.
Sir, I have a question.
Yeah.
Can you give me a little bit info about the quantifiers?
Oh, we'll get to that, to quantifiers next time.
Next time, okay.
Yeah, they're coming up. All right. Oh, and by the way, if you're looking to move, like go further along, like and get ahead, I would watch those YouTube videos. In particular, the first link in the YouTube videos folder, the video series on discrete math. You can probably find an answer to information about the topics that you're moving on to ahead of time just by looking at those lectures. Like I will get to them, but if you're moving ahead, go ahead and watch those lectures.
I have a quick question on the homework. So as you complete each activity in the book, does it automatically submit to you?
Yes.
Okay, thank you.
Okay. Well, if that's it, everyone stay safe, and I look forward to our next lecture. All right.